So, in the last several classes we have been looking at adaptive equalization. So, what we need to do adaptation according to the LMS algorithm is the error between the received signal out of the equalizer and the target signal, as well as we need access to the gradients. This is the reason why it is hard to adapt the equalizer when it's at the transmitter. We don't have access to the gradients. Okay. So, we only know the error and it's hard to figure out what to do to the transmit equalizer. Okay. When the equalizer is at the receiver, we have access to the gradients and we can do the adaptation. So, just we'll finish up today with this adaptation after dealing with some practical issues. So, even though it's easy, because it's at the receiver, still you need additional hardware in order to get the gradients. Okay. The easiest case is when you have an A to D converter and you implement everything in digital, then you have all signals as digital, that is sample data signals, then you can get the gradients and any quantity that you want. The circuit may become complicated, but there is no problem accessing those things. So, let's say we implement the receive equalizer using sample and hold circuits. So, typically what you would do is something like you make differential implementation. So, you use two sample and holds for the input and the output. Okay. And you need a buffer after each stage and so on. Okay. You can have multiple buffered sample and holds in cascade. Let's say we also have a buffer here. Okay. Then we generate the weighted summation by, the easiest thing is to use transconductors and add up the currents. So, we get in this case GM1 times the sample here plus GM2 times the sample here plus GM3 times the sample here times some resistance to be the output voltage. Okay. So, the output is, this is now a 3-tap FIR filter in the analog domain, in the analog sampled domain. This is a sample and hold circuit. This is not yet complete. I will come to that later. Okay. So, this is essentially how you have to build it, and all these sample and hold are controlled by a certain clock, and this clock could come out of the clock recovery circuit, okay, which comes after the equalizer. So, this is the output of the equalizer, and you have to make these GMs variable to make a programmable or an adaptive equalizer. Okay. What happens if the buffer gain is not exactly 1? I mean, how would you make a buffer? What are the different ways in which you can make a buffer? Source follower. So, some amplifier whose gain is nominally 1, that's usually what you end up using for a buffer. The input impedance should be high, that's the criterion, right? Now, if you make an NMOS source follower, you know the gain is not going to be 1. Even a PMOS source follower, the gain will be different from 1. So, what happens? Will the circuit work even in that case? Yeah, actually it's not a big problem, especially because we are dealing with an adaptive equalizer. So, we wanted, let's say, x of n minus 1, x of n minus 2, so that we can multiply these with C0, C1 and C2 and add them together, right? This is what we wanted. Now, instead of x of n, you get, let's say, alpha 0 x of n, alpha 1 x n minus 1, alpha 2 x n minus 2. To get the same transfer function, you will have to scale this by the corresponding alphas. And when you have adaptation, that part will take care of doing this automatically, right? So, the adaptation doesn't care that, oh, this is not exactly x of n minus 1, but it is some scaled version of it. it only tries to move the coefficients in a particular direction until you get the output error to be as small as possible. That is, the mean square of the output, mean squared error at the output is small. Okay. So gain of the buffer is not an issue, but if the gain becomes much smaller than 1, the problem is these GM values have to be large to compensate for it. So that becomes an issue. That's a more of a practical issue. It's not that the equalizer won't work. If you make a much larger GM, it will work, but now you have to realize a much larger GM simply to compensate for the loss of the equalizer, loss of the buffer. And typically you don't want to attenuate the signal and then amplify it, because if you have noise added at the attenuated point, that also gets amplified. You would like to keep the signal level constant. That is a better situation than, let's say, making the signal very small and amplifying it up to the original level. If the buffer gain is not exactly 1, adapting the coefficient takes care of appropriately scaling the GMs. So that part is okay, but if the gain becomes much smaller than 1, you will have to realize a much larger GM. Now the sample and hold circuit. Is the stuff that I showed sufficient? What will be the control waveform of the switch? The clock. So the clock looks like this. If this is T, the clock can be of this form, right? It is high for T by 2 and low for another T by 2. So is this okay? Can I cascade these things? So let's say this is clock, and then I have a buffer. I have another one. Okay. So this is, let's say this is clock and this is clock bar. That's what you are saying, right? Okay. Now what is the delay between this sample and this? T by 2. So but that's not what I want, right? At least in the original structure I wanted a delay of T. So what do I do? So actually I need to use this entire unit as a single sample and hold. Okay. So between here and here it has a delay of 1T, isn't it? So this entire thing gives me a delay of 1 clock cycle. So I have to use here in the previously I just wrote this as a sample and hold, but this needs to be a cascade of 2 buffered sample and holds, so that it gives a delay of T. Okay. Okay, so you are saying you will operate this with half a clock cycle. I mean 2T. Yeah, that also can be done. This is sampled at the level, right? But when the switch turns off is the sampling instant. Okay, so you have something like this. So if you have this waveform going to the switch, it will follow it for some time and do this thing, right? So basically the value that is stored, this value is the instant at which the switch opens. So it is transparent for half a clock cycle, but the sampled value is when the switch opens. So now let's, if we look at the waveforms in a cascade of 2 sample and holds. So let's say this is the input signal. Okay. And let's say this is, each of these marks is half a clock cycle. Okay. So it follows it for the first half, then holds it, then it follows it here, then it holds it, then it follows it, and so on. Okay. So this will be the output of the first sample and hold. The output of the second sample and hold is, it follows it here and holds it, then it follows it here and holds it, it follows it and holds it and so on. Okay. So the output of the second one basically is a constant waveform for the whole cycle in the ideal case. In reality, what happens is to switch from one to the next, it's not instantaneous, so it takes some time. Okay. So this is a sample and hold, and if you put it through another set of the same stage, the entire waveform will be delayed by one clock cycle. Is this okay? Okay, a suggestion was instead of using two sample and holds, we will use a single sample and hold with twice the period. Instead of using this waveform, which forces me to use two of them to get a one clock cycle delay, I will use this. Will it work? Will this work or no? It will work. How often are you sampling with this? Huh? At best by 2, right? So that is the problem. So you can't use it directly like this. So what happens is here, when let's say the switch is on when the clock is high, so you are taking a sample here and the next sample is here. Okay? And this sample is held for this entire period T, but your sampling rate is half. So if you choose to use something like this with half a clock cycle, with half the frequency, what you have to do is you have to have a sample and hold with clock, where clock represents this waveform. You have to have another sample and hold driven by the same input and sampled by clock bar. Now these two will give you alternate samples, and perhaps you can multiplex these two, okay, using an analog type of multiplexer. So at the output you will have a waveform which is held for the entire period T, okay, and it's also the sampling rate of that is 1 over T. Okay. So you will have to do this. So that is another way of making a sample and hold which samples every T seconds. Yeah. Yeah. Yeah, you are getting samples here at the falling edge of the clock because of this, and you are getting these samples because of the bottom part, which is what you want. Yeah, that's right. So, firstly, a circuit like this, okay, this circuit is known as a track and hold. That is, it tracks for half a cycle and holds and so on. By cascading two of these, you can make a sample and hold, when you say sample and hold, you interpret it as when the clock edge arrives, it samples it and then holds that value. Okay. By cascading two of these, you get something like a sample and hold. Similarly, by having two track and holds operating at half the rate and multiplexing the output, you can also get a sample and hold. Okay. So there is no tracking part that is visible at the output of the multiplexer. Okay. Yeah, you will have to use it, meaning when this clock is low, it should let this through, and when this clock bar is low, it should let this part through. Okay. Now, how do we evaluate the gradients? Let's say we are using sine LMS, right, for simplicity. Even that may be difficult enough. So we have a sample and hold based equalizer. So we have a sample and hold. When I write something like this, it's assumed that inside there are two track and holds in cascade, or maybe two track and holds operating at half the rate in parallel. Okay, one of those two. So this is the idea, and then you take these three, sum the outputs. Okay. So I am showing a single-ended realization, but typically at high frequencies, all realizations will be differential. This is just a kind of halfway between a schematic and a block diagram. Now I take this, pass it through a slicer to get y hat, and I also know how to get the error I said that you can't really subtract the input from the output. Typically what you do is you subtract +1 and you slice that using a flip-flop to get sign of y minus 1, and similarly you can do another thing for sign of y plus 1 and you pick the appropriate one based on y hat, that is. Okay, so basically somehow or the other I found out the error, right? I have the error, now I need the gradient. What do I do? How do I find the gradients? Where are the gradients in this? So these are the gradients. This is one of them, this is the other one, and this is the other one. And that's what I need to multiply with the error to get the adaptation. I mean the coefficient updates. Okay. So if I had an analog multiplier, I can take this value, multiply it by the sign of the error and do it. So that would be equivalent to updating the coefficient by sign of E and x of n minus k. So you can take the sign of either or both of them. Okay. So this will also do the updating, but this needs an analog multiplier. Or does it? Yeah, so that's what essentially we want to do. Okay, so the sign LMS can be expressed as saying you want to increment or decrement the coefficient by mu based on the XOR of the gradient and the error, or the product of the sign of the gradient and the sign of the error. Okay, so that's what I want to do. So how do I get the sign of the gradient? I don't want to use analog multipliers, let's say. So at each of these points I need also a slicer to get, this gives me sign of x of n, sign of x of n minus 1 and so on. Okay. I need more comparators in order to do this. Then I can take this one and XOR with this to get the coefficient update. Okay. And of course all these are clocked comparators. So this one and this one, and the clocking of this and the clocking of the sample and hold should be synchronized in some way. Okay, so that you get the sign of the right values. So the problem is now the buffer is getting loaded by the comparator as well. So that can be a bit of an issue. Okay, so this will work. This is how you do it if you follow the if you just follow the algorithm and try to implement it, this is what you come up with. Is there something else you can do? Essentially the problem here is I have to load all the buffers with these comparators and I would like to avoid that. Is there a way to do that? Can I remove those comparators from Yeah, what do I do then? So actually, see, if you look at this is simply a delayed version of this, and this is a delayed version of this, and this is a digital signal. So I can delay that using flip-flops. Okay, I don't have to load these points and determine the sign. So that's the idea. That's all. So I can slightly optimize the circuit by removing these comparators. So let's say my continuous time input was here. I have sample and hold. Instead of drawing two blocks, I will show the buffer also inside this. So this is my data slicer. I get y hat and y, and I can also determine y minus y hat. I don't imply that you subtract y hat from y directly like this. There are other ways of doing it which we have already studied. That is, you subtract a fixed quantity from y and slice that. Okay, this is E. And in fact, you don't do this. You take the sign of E. Okay, and if you had comparators here, you get sign of x of n. So let's say this is xn, xn minus 1, xn minus 2. Okay, and with using these, I can update GM1, GM2 and GM3. Okay. So I take the XOR of this and see whether to decrement or increment this. Similarly for the other two. Yeah. Yeah. But how will you do that? You have to multiply. Yeah, that's correct. So, see, when you say, you are saying that instead of using minus mu sine of e sine of x n minus k, you will use minus mu sine of e x of n minus k. So, this is the increment in the coefficient. So, if you do this one, you have to have much finer control over the GM, because the update in GM is not a fixed value mu. In the first case, the update in GM is a fixed value mu. Okay. In the second case, the update in GM is mu times xn minus k. So, you have to have a facility to vary GM in either much finer steps, so that you can do it in mu xn minus k, or you have to do it continuously. Okay. The current which comes out of what? So, this one. Okay. So, this is xn times GM1, yes. Yeah. No, that's what. So, in one case, the GM1 is simply incremented or decremented by mu. That can be realized by having a GM which is switched, right? Just like we discussed for the transmitter, you can imagine GM being made of a number of cells which are connected in parallel. Some cells are turned off if you want to reduce the value of GM. Okay. In this particular case, this represents a continuous variation of GM, right? This mu times x of n minus k. So, you have to have a way of varying GM continuously, and by just not continuously, but by some predetermined continuous way. That is more difficult. Okay. Essentially, if you want to do that, you need an analog multiplier. You can't have the switched stuff. Is that clear? So, the alternative was, instead of having 3 comparators here, okay. So, instead of having 3 comparators, I will have just one, and then use flip-flops to delay this. Okay. So, this gives me sin x of n minus 1, and this is sin of x n minus 2. Okay. So, that is a slightly better case than the previous one, where every flip-flop, every sample and hold was loaded by a flip-flop. So, this is how we would realize an analog receive equalizer. This is one of the ways of doing it. What was the other way of making an analog equalizer in the receiver? Not using sample and holds. Huh? No, ADC, yeah, that's a digital one. So, transmission line, that was the thing. Yeah. Why not? Yeah, so we may have to use a cascade of NMOS and PMOS source followers. Okay. Sine and so we discussed that, right? The trajectory it takes. If you take the sign of the gradient, it takes a different path. So again, I forgot to look up the references to see if it can lead to non-convergence in some cases, but definitely it takes a different path for convergence. And whenever you take the sign, the final coefficient is not adjusted so finely, right? So if your minimum of the error square is here, you cannot settle to that value with the sign algorithm. You can only settle to, I mean, there is no settling, there is kind of a limit cycle oscillation between points which are on either side of the minimum. So the actual error that you get is more than with the sign than with the full LMS. Those are the differences. Yeah. Okay. So the question is, I want to change the sign of the tap. How could I implement that? What can I do? No, the sign of the tap should be, so in this case, so let's say this is X and I take this to be my output Y, okay, and by varying the tail current or by doing some other things, I can change the gain, but it will always be positive, okay. Y by X is variable but always positive. So the question is, how do I make it go from negative values to positive values? I want both negative and positive values. If I wanted only negative, then that's silly. I mean, I just flip the sign of Y and I do that. So if I want both positive and negative, what do I do? 2 input, 2 output MUX. Where is the MUX? A MUX usually has 2 inputs and 1 output, right? What is the 2 input and 1? No, the output is already differential here. So, like you can switch, you can do it in various ways. So, firstly, so you can have this kind of cross connect. So, based on some control, it applies the input directly or the same thing flipped. So, that I can do potentially with 4 switches. So, if these 2 switches are on, I get the direct connection. And if these 2 switches are on, I get the cross connection. Okay. So, this can be some control C or let's say D and D bar. Okay. So, this can be done. The only challenge here is for the input common mode voltage, whatever the input common mode voltage is, the switches have to work properly. The switches will introduce some resistance in the series path. So, that is a potential problem with this thing. And you can use this either at the input or at the output. So, that is one way to change the sign. What else can you do? The opposite one, yeah. So, an alternative is to do something like this. So, you apply X to this differential pair. You apply X to another differential pair. But these are connected in reverse. Okay. And I also have, let's say, I vary this with a controllable current source. Okay. Now, I make it such that this is, if this is some I, this is some constant I naught minus I, and I itself varies from 0 to I naught. When I is 0, this part is cut off, this is active, you get the maximum negative gain. When I is I by 2, I naught by 2, then both sides are active with a tail current of I naught by 2. So, you get a gain of 0. Okay. And when I equals I naught, this is on and this is off. So, you get the maximum positive gain. So, that's also possible. Yeah, what's the question? If yeah, definitely. Yeah. So, when let's say I equals 1/4 I naught, so this will have 3/4 I naught. So, you have a larger negative gain than a positive gain. Okay. So, the total GM of this stage is the difference between the GM of this and the GM of this. So, you do go through many steps between the two. It's not as though you only go between I equal to 0 and I equal to I naught. But the gain varies from the most negative value to the most positive value. Yeah. No, this is a single tap, but the tap value is, maybe it goes from, let's say, -half to +half, right, in some steps. It can't go in a single step, then that means that the value of mu is very large. You can't implement that while being stable. So, maybe, let's say, you want variation between -half to +half in steps of 0.05, okay. So, in that case, each of these current sources will have to be a combination of parallel devices. Okay, we have already seen how to make a variable current source in digital steps. So, you use one of those methods to make this current source parallel, but then the digital control you provide to each of them, you arrange it such that this variation is complementary. If one of them is I, the other one is I naught minus I. Okay. Is this clear? Or no? So that's how, so some of the tabs you may have to realize both positive and negative values, and this is what you have to do. Okay. Yeah, that's correct. Yeah, so there is a problem here. Firstly, if we change the tail current, the linear range of the transconductor is also changing. So there is definitely an issue with nonlinearity. You just have to simulate it for your particular input voltage and see if it is linear enough. Okay. You degenerate with resistors. That's an idea to make it linear. What happens now? Will there be a... So now the GM won't vary. Yeah, okay. So there are other ways of doing it. Let's not go into that now. So the idea was, okay, you do a degeneration, and that's a completely different way of varying the GM. So while his point is, now if you reduce the current, the linearity of this differential pair reduces. Okay. So one saving grace with this type of structure is, let's say this current is very small, I is small, then I naught minus I is large. Now the linearity of this differential pair is poor, whereas the linearity of this is good. And this is contributing most of the current. So it is not very bad, but yeah, there is definitely some issue with linearity. Okay. You still have to make sure that it is linear enough for you. But the thing is, when one of the currents is very small and the linearity is poor, it is also contributing a small amount of current. So it turns out that when I is very small, it is still linear enough because the other part, which is contributing most current, is linear. Okay. So if you had a single differential pair where the tail current was varying, then as the current becomes very small, the linearity really goes to pieces. Whereas in this particular case, when this current is small, the other current is large, so the linearity is not too bad. Okay. So yeah, there can be other ways of varying the GM. So you have, let's say, a differential pair degenerated by a MOS resistor. By varying the gate voltage, you can make it variable. So you can either, by varying the gate voltage continuously, you can make it continuously variable. Alternatively, you can have a number of devices, you either turn them on or off and make it also variable. Okay. So, and you can come up with other circuits as you work with the whole thing. Okay. Any questions on any of this? So there are a lot of details in implementation that you have to go through while making an adaptive equalizer. Even when making a receive equalizer, but particularly when you are making it adaptive, you have to make the coefficients variable. And you will always have to do like more things like limiting the range and so on. So for instance, one thing that could be risky is, let's say you make all the coefficients variable over a wide range. So somehow it goes and gets stuck where the coefficient is 0 or very small. Then the output signal you get is also 0. Okay, then you can't do any more adaptation. So those kind of things you have to avoid. Okay. So for instance, so let's say you have GM1, GM2, GM3, all potentially variable between negative and positive values. But for either because of a wrong startup condition or because of something, they get stuck at 0. Then you have no Y. So then you can't really do this very well. Okay. There are lots of practical issues with making adaptive equalizers. Huh? Circuit delay. No, I said, so stuck at 0 meaning, okay, let's say initial condition, very like, this is a totally bad case, but you initialize the GMs, when the chip starts up, all these are set to 0. Okay, that is, so circuit starts up where, let's say this is the method of implementation, this equals I by 2 and this equals I by 2. So then it will be at 0 and maybe you will not be able to compute the error properly and drive it in the right direction. Okay. Yeah, so you have to work out the reasonable range of coefficients that you want, and also you have to set it up so that the chip, when it starts up in a reasonable condition. So if you look at the assignment that I just gave, I said that C0 is 1 and all the other coefficients start with 0. So that way you will ensure that at the beginning there is no equalization, but there will be some signal that's coming out of the equalizer. Okay. So the equalizer is behaving like an amplifier. If C0 equal to 1, it's just a buffer. So one last thing. So I talked about continuous time FIR filters. So you have transmission lines of delay T. Okay. And again you use the same method of linearly combining them to form the equalizer. So in this case, to get the gradients out, you have to use comparators here. Okay. And you put this to a slicer and also get the error. So this is what you have to do. Can you do the other method of delaying this? The output of this is digital. Can you delay it using flip-flops and use that as gradients? So the problem is actually that the delay of the transmission line may be nominally equal to one period, but it can vary quite a bit in fact. If it is different from T, now if you obviously this is not exactly 1T delayed, so this is not 1T delayed version of this. Okay, it will be the sign of this, but it's not 1T later than this one. So you have to use comparators. Actually, this is a pretty complicated practical problem. The principle is very clear. I mean, there is no difference between this and anything else that we discussed. But so far, nobody has made a high-speed equalizer in which this LMS thing works properly without some other external aid. Usually, you have some other measurements also you have to make to get the whole thing to converge. It's not very easy to get this to converge. Okay. So in practice, also you now start loading the transmission line with flip-flops and so on. So that becomes very complicated, and if you do a lot of that, the equalizer may not work. So to get a high-speed continuous time equalizer working with LMS adaptation, that can, without doing some other fiddling with it, that is a difficult thing. And so far, I mean, I have not seen an implementation, let's say at high speeds of 5 or 10 gigabits per second. Yeah, that's true. Again, the problem is a practical one. The transmission line already was very large. Now you are saying you will use a transmission line for the gradients also. So that is a very suboptimal solution because you will use a very large area. Okay. Yeah, first of all, this transmission line is a lumped approximation. So you use on-chip spiral inductors and capacitors to mimic a transmission line. Now, if you have to do that for the gradient also, it will be a problem. And secondly, there will still be a mismatch, right? Between your two physically different transmission lines, there will be a mismatch. So, any questions on receive equalization and adaptation? So, the assignment that I sent out yesterday is to deal with that. Of course, there is no implementation detail. There are no transistors in this assignment. It's just to play around with the LMS algorithm and see how it converges and so on.